Yeah, sure, I started. Hey.
Okay.
Good afternoon, everyone.
Good
afternoon. Okay. So
Good afternoon.
I will reintroduce. I think we'll start. My name is Chawanzi Mudenda, and I'm in Setat. I'm at the FST. I'm doing GGM, and I'm in my first year. So I'll be helping you guys with electrostatic and electromagnetic Navid. So basically, electrostatic is the one the BCG guys do. So there are two modules, but they have the same, almost the same content. So that's why we have been allowed to actually teach them together. Yes. So on the timetable, it's written I'm taking 4 filiers. That's APESA, GGM, 5 actually. APESA, GGM, BCG, MIP, ENSA, and ENSAM, and SVT. So I was corrected to say APESA doesn't take this kind of physics. So if you're doing APESA, you can leave or whatever you decide to do. But yes. So we're going to start. So I'm going to tell you a little bit about electrostatic and electromagnetic. So basically, electromagnetism is a branch of physics that studies the interactions between charged particles electrically, whether at rest or in motion. Yes, so it's a study, or it can also be a study of electromagnetic field and its interaction with charged particles. Hello? Is anyone saying something? Okay, so I continue. So basically what we're going to do today is just going through. So this chapter 0 that we're starting with is system, de coordonnées, and vectors. This please, can you put your microphone? Check. Try to mute it. It's on. Okay, so I continue. So basically, this topic that we're going to do, system, de coordinate vectors, it's found in Mechanic 2 as well, but I haven't yet done Mechanic 2, so I'll just try and run you guys through it. But it's more detailed in Mechanic 2, but we need some expressions, and yeah, as we go on with our module. So we're going to start system de coordinate in vectors. So this is, we're going to start doing with repair d'espèce. So what is a repair d'espèce? A repair is un système de coordonnées, il sait à décrire le mouvement. So system of coordinates that is used to describe movements. Yeah, basically that's it. So there are, in mécanique du bois, in more detailed physics, there are 4 kinds of repair. There's the repair Cartesian, the repair cylindric, and the repair spheric, and the repair definite. But in this module, we're just going to look at the first 3. So we move. So we're going to start with talking about the repair Cartesian. And you need to be a bit more visual, because this is more visual, like you need to be visual for you to get a better understanding of this first part. So I'd advise you maybe to grab a pen or a paper and something just to write on. Yeah, so, and I forgot, if you have any questions or queries, you can just raise your hand or unmute your mic, and I will answer you before we move on. If you have any question, just unmute your mic and ask me, other than you being left behind. The rest of us move. So yes, so we're going to start with the repair Cartesian. So we're going to start by, just a minute, we're going to start by describing, not really describing, but these expressions, we have OM, vector OM, DOM, DV, and DS, vector DS. So we're going to kind of discuss and explain to each other how we got to this expression, and yeah, we'll move from there. So yes, let me, okay. So yes, so we're going to start with OM. So I've got a drawing here. That's, I think you guys, most of you guys have come across it. So usually in Zambia we have a plane, but in this case we have a 3-dimensional plane that includes X, Y, and Z. So in repair Cartesian, we've got 3 bases. So we've got 3 axes, that's X, Y, and Z. And then along this axis, we've got a base or unit vector applied to each axis. So on the x-axis, we've got the EX base vector. Along the y-axis, we've got the EY, and along the z-axis, we've got the EZ. So you can also, these base vectors can also be represented by E cap, J cap for Y, and K cap for Z. So we're going to first describe our OM and how we got to our OM. So basically, we're just trying to find the vector. We're trying to get to the vector OM. Just a minute. Trying to get the vector. Okay. So we're trying to get the vector OM. So how do we get the vector OM? Let me just try to draw it. How do we get to the vector OM? Yes. So how do we get to the vector OM? So I have indicated H and H prime, and then we've got our O as the center. So point M is any point. You can pick any point. Point M is point quelconque. Any point you pick, and it's in 3-dimensional. It's in. So how do we get the vector OM? It's a vector OM. So the vector OM, we can either get it by moving from we get it either by moving from O to H and H prime, or from O to H prime and H prime to M, or we can get it from moving from O to H and H to M. Yes. So what you need to mind is that H prime of M is parallel to O, and so H prime of M is the vertical representation of OH. The same with OH prime and HM, they are parallel to each other, so meaning they're the same. So we're going to move on. So OM can either be represented by going like this or by coming like this. So we're going to move from O to H, or from O to H prime, whichever I choose. So we're going to move from O to H. So from O, for you to have the point H, we're using the horizontal axis. So we're using X and Y. We're plotting it using X and Y. So for us to have H, we've moved X direction. We've moved X direction in the X axis and Y direction in the Y axis for us to get the point H. And then for us to get to the point M, we've moved H direction. We've moved K direction in the direction Z. So for us to get the point M, it's a combination of the direction of movement of X in the X direction, Y in the Y direction, and K in the Z direction, or EZ in the Z direction, for us to get our point M. So what we have here, OM is equals to H prime of M plus OH, which is H prime of M plus OH, is basically, since we've agreed that H prime of M is a vertical representation of O and H. So we have, for us to get to H, we added the direction of X. We moved in the X direction in the direction of X, and Y direction in the direction of Y, which will make us have X in the direction of EX. So the base, you do not have to forget the base vectors when you are representing your vector. So we have to know them back per K. So in the Cartesian, our base vector is EX, EY, EZ, or in other books or other leaflets or other polycops, they use I cap, J cap, and K cap. So yes, so we've moved X direction in the direction EX and Y direction in the direction EY, plus Z direction in the direction, Z direction in the direction EZ. So we have our answer, which is X, EX plus Y, EY plus Z, EY, Z, EZ for us to get OM. So here was just my indication in case I missed it. So the H is, the H is the projection of M in the plane XOY, which is here in the direction X and Y, in the plane X and Y. And then the H prime is the projection of M sous l'axe vertical. So are we clear from there, or there any questions? There's some questions. Okay, so I believe that.
Just a minute before you proceed.
Okay.
Just repeat there on the equation how we came about with
How we
X,
came
EX, and all that.
Okay, so I said, just a minute. So I said we're trying to find the vector OM. Sorry about my drawing. So yes, we're trying to find the vector OM, right? So how do we get to OM? There are two different ways. So you can either go from O to H prime to M, or we can go from O to H to M, right? Then I've explained saying H prime to M, the movement of H prime to M is a vertical representation of from the movement of O to H. So they're the same. Is that, yeah. And then what else? And then from O to H prime and to M, okay. Okay, yeah. From O to H prime and from H to M, they're parallel, so it's the same. So this, what can I say? H prime is the projection of M sous l'axe vertical. So on the axe Z, H prime is the presentation of the point M on this axe. So what I said is that for us to have the vector OM, we can either move using the two directions. So I chose to move from O to H plus H to M. Yes. So when I moved from O to H, I said for me to have the point H, I've plotted it in the XY plane. Right, that's what the math that we usually do in Zambia. For you to put a point on the XY plane, you have to use the X coordinate and the Y coordinate of that point. So don't forget that H is the vertical representation of, it's like M that has been projected downwards. That's why I said you have to be a bit visual. So yes, so for me to have the point H, I have moved X direction, or I mean Y direction in the direction EY, and I've moved X direction in the direction EX for me to have the point, this point right here. So having that, so I know that just for me to move from O to X to H, I have X EX plus Y EX, EY, I mean. And then for me to move from H to M, this is along the car axis, because we've concluded that these and these are parallel. These and these are parallel. So this is the car axis, and this can also be regarded as a car axis. So for me to move from H to M, it's along, I have to move Z direction in the EZ. I have to move Z. I have to move a certain direction in the EZ direction. Is that clear, or I should?
Oh.
Well, the people.
I have a question.
Okay.
Is this in a 3-dimension, or we're just talking
Yes.
about an ordinary Cartesian?
No, this is not an ordinary Cartesian plane. I say we're dealing with a 3-dimensional plane. We have Y and Z. Is there anything else? X and Y and then M is any point that you plot in the same plane. So we choose any point M, and then we try to find an expression for the vector OM and how we got the vector OM, the expression for the vector OM. And then I said that we have 3 axes. We have the X axis, the Y axis, and the Z axis. So along this X axis, we've got the base vector EX, the direction of the base vector EX. And along the Y axis, EY. And along the Z axis, we've got the base vector EZ. And then you must know this packet, because each repair has got its own base vectors. So in the case of Cartesian, we've got X, EY, and EZ in that order. Or sometimes they can use E cap, J cap. So for me to get to the point M, either I move from O to H prime to M, or I move from O to H to M. And then I said for us to get the point M, we've projected it downwards in the plane XY. So we've projected our M in the direction K in the plane XY, which is our point H that we have. So H is a projection of M in the X or Y plane. So for me to get the point H, for me to get the OM, I said I can either move like, or move like this. So OH, for me to get O, I have to use the normal X or Y way of plotting a coordinate. So I have to add X in the EX direction, Y in the EY direction, X in the EX direction, plus Z in the EZ direction.
Okay.
Yeah, so that's how I got my OM. I added OH, which is X, EX plus Y, EY plus the upward direction that I had to move for me to actually get to M, which is Z, EZ. Still not clear?
We're clear.
Huh? Hello? I need you guys to move with me. Still not clear, still need...
Okay, can you just put a bit more emphasis on the z-axis?
On the
I
Z...
think new on the z-axis.
What?
The z-axis.
Oh, the Z-axis. Okay.
Yeah.
So, okay, you guys have you guys come across, okay, no, this is obviously first time, but this is a 3-dimensional plane. So we have the x-axis, the y-axis, and the z-axis. And then we know that lines in parallel are the same. So OH, where is that? Just a minute. O, oh my, okay, yes, OH prime and HM prime are running in the same axis, which is Z, because they're parallel. And that's what I said also about H prime, M, and OH. They're parallel, so they've got the H prime of M is just a vertical representation of OH, so to say. And then for me to get to the point M, H is not my point M. H is just the horizontal representation of M. So for me to actually get to my M, I need to move a certain direction up. I have to move upwards in the direction EZ. Is that clear?
Yeah, I understand. But do they always give this point, like is it?
Is there?
Are the points always given?
Yeah, they always give you a point. They always give you a point. Yeah.
All right, then. Thank you.
Okay. So this was just explaining, that's why I chose any point M in the plane, but they always give you a point. So we move on. We talk about the gradient. So the gradient in coordinate Cartesian est défini tel que dv. So this dv is not, usually dv, when they say dv, they mean the change in volume.
And she bought bundles. She bought bundles. Now that means I can see you, okay?
Hello, can you please, Mike? Yes, so this dv, usually when they say dv, they're talking about differentiation in volume or the change in volume, but this dv is actually represented by its Champ scalar. So Champ scalar is a scalar field. A scalar field is a function of several variables which associates a single number of scalar with each point in space. So you need to know this package. Some of these expressions, you need to know them package. So we've got dv, which is Champ scalar, is equals to grad v dom, and the expression for gradient is this change in, usually we have gradient of v. So if we have gradient of v, we have v here, we have v here, we have v here, but this is just a mere expression of grad. So we have change in ex over dx, change in ey over dy, and change in ez over dz. And then we have actually two expressions of dv. So we have dv as expressed as grad v times dom. So the multiplication of grad v times dom. So if you have this expression, if you know this expression, if you're given the gradient, if you're not given the gradient, you can calculate it if you're given dom and dv by just dividing dv by dom. Or if you have gradient of v and dom, you can get dv. Sometimes they can ask you to calculate dv. You can get dv by multiplying the grad of v times dom. Yes, so it's represented twice. You can represent it as dv is equals to grad v times dom, or I actually forgot to add the other way you can express it. So let me just go to the other slide. Or it can be represented as this, but this is in coordinate cylindric. So it's the same expression. dv can be expressed as grad v times dom, or it can be expressed as dv, change in dv over dp times this, changing this over this times this, changing this over this times this. So this symbol is a symbol representing partial differentiation. So I'm sure most of the people who took ADMA, they know the symbol, partial differentiation symbol. So in this is in coordinate, but in coordinate Cartesian, since we have x, y, and z, here it will be dx, dy, and dz. So we have two expressions of dv. We have dv is equals to grad v times dom, and we have dv is equals to this in coordinate Cartesian, we have dx, this times dx, this times dy, and this times dz. Any questions?
Yeah, there's a question. Yeah, could you kindly explain how they came about with how they find the gradient?
How they found the gradient? Well, you have to do that. It's a long process, so you have to do that in mécanique du poids in details. Yes, but this is simply the final gradient expression for coordinate Cartesian. Yes.
So does that mean we have to know it by heart?
Yes, you have to. Our professor actually taught us to know them by heart, because you have to know the gradient expression expressed in coordinate Cartesian and coordinate cylindric and coordinate spheric, and they're all different.
All right.
Yeah. So yeah, so if you have dv, and dom, you can find your grad v. If you have dom and you have, if you don't have grad v, you have dom and dv, you can find your grad v. So this is the mini table that I used, or that, yeah. So this is grad v, this is dom, this is dx. So as I said earlier, for our dv, it has two expressions. So it can either be expressed as dv is equals to grad v times dom, or it can be expressed as dv over dx. Let me go to it. So it can be expressed as, sorry, I actually forgot to put that there. Or it can be expressed as this. But the only difference is that this is coordinate cylindric. In coordinate Cartesian, here we have x, y, and z. So in coordinate Cartesian, we have change in partial differentiation of v over dp. We have times dx. Partial differentiation of x over dx times dx. Partial differentiation of v over dy times dy. Partial differentiation of v over dz times dz. So this is just a simple table on how you can, where am I? Okay, yeah. Simple table on how you can get the three expressions just by, so we have on our DOM, let's explain how it's used. On our DOM, we haven't explained about DOM. So on our DOM, we have, DOM is the change in OM. So DOM is the differential, is the derivative of OM. So a change in OM is equals to a small change in X in the direction of EX plus a small change in Y in the direction of EY plus a small change in Z in the direction of EZ. It's just as simple as that. So there's no really much mathematics that you need to do. So OM is equals to X in the direction of EX plus Y in the direction of EY plus Z in the direction of EZ. And DOM, change in OM, a small change in OM is equals to a small change in X in the direction of EX, a small change in Y in the direction of EY plus a small change in Z in the direction of EZ. And then this V is a representation of a change in volume. Unlike this V, I said this dV is Champ-Scaler, but this dV is change in volume. So volume, I think like everywhere, usually volume we are calculated by multiplying the length, the base, and the height, which is the same. So we just look at our DOM expression. We got the small change in X times the small change in Y times the small change in z. And as you have seen on dv, there's no the representation of a vector because volume is not a vector. Yes, so it doesn't have it doesn't need to have direction like the ex, the ey, and the ez. So simply you just multiply the change in x, the change in y, and the change in z to get the change in volume. And then this is the change in surface area, which is like surface area, change in surface area. So unlike dv, it's got direction. So what we do to get this expression is, and I think I really need you to follow me here because if I don't get it here, it will be hard to get it in the other repairs. So for us to get this expression, ds has direction. So now we have to go back to, we have to know that we have to express it in ex direction, ey direction, and the ez direction. So we're going to differentiate dv. Yes, we're going to do a partial differentiation of dv. So our expression of dv is dx times dy times dz. But we know that ds is supposed to have direction. So we differentiate this in reference to x, y, and z in the direction ex, ey, and ez. So the differentiation of dx times dy times dz in reference to x in the direction ex is equals to, so if we differentiate dx times dy times dz with reference to x, the differentiation of dx is going to be 1. So we're going to, it's like partial differentiation is more like the product rule, in that when we differentiate one, the other remain as constants. When you differentiate the other one, the other remain as constant. When you differentiate the last one, the other remain as constants. So in this case, we differentiate this guy, this whole, we partially differentiate x, just the x variable. So we differentiate with respect to x, and then these two are going to remain as constants, and then the differentiation of this is going to be 1. So we take it as 1, as it is here. So we take it as 1, and then in the direction of ex. And then the same happens when we differentiate dv with respect to y in the direction ey. So what's going to happen is that these two are going to remain as constants. This is going to give us y in the direction ey. The same happens for the last part when we differentiate dv with respect to z in the ez direction. What's going to happen is that these two are going to remain constants, which is dx dy times that we have here. The differentiation with respect to z is going to be 1 in the direction ez, which is what we have here. So are there any questions up to here? Hello, are there any questions, or I continue?
No.
Okay, what's your query? Oh, there are no questions. Okay, then we continue. So I hope you really get how it's coming up with this. So on the ds, usually when we have volume, for us to get surface area, we have to differentiate the volume, which is exactly what we're doing here. So we have an expression of volume, and then we have ds, but ds is a vector, unlike the volume. So we have to differentiate it and not forget the direction. So in coordinate Cartesian, we have ex, we have the base vectors of direction ex, ey, and ez. So we're going to differentiate v, partially differentiate v with respect to x, y, and z, each one on itself. So the first one, what we did is that we differentiated it with respect to x in the direction ex. So when you differentiate dv with respect to x, this guy here is going to give us 1, and then these guys are going to remain as constants. So our first one would be dy times dz in the direction of ex. And then when we differentiate this guy with respect to y in the direction ey, we're going to have dx times dz in the direction ey. And then the last part, when we differentiate this guy here with respect to z, we're going to have dx dy in the direction of ez. So Yeah, we move on since there are no questions. Yeah, so as I was explaining about the gradient, this is the expression for gradient, this is the expression for dV. I said there are two expressions for dV. So this is a mini table in which you can get the expressions. So we have our grad V, our DOM, and our dV. So we have our expression of dV that I explained. So dV is change in V over change in X times dx in coordinate Cartesian, change in V over change in Y times dy, change in V over change in Z times dz. And then our DOM is dx E dy times EY, and dx times Ez, which is here. I don't know if you guys can see, which is here, our DOM. So I've just gotten the dx, the dy times dz, which is what we have here. Here, the dx times the ex, the dy plus times the ey, the dx times the ex. And then we've got our gradient, our expression for gradient. Then if you are finding the gradient for f, gradient of v, so here I would express it as gradient of v. So if I have gradient of v, here I'll have a v, change in v over dx, change in v over dy, and change in v over dz. If you have if you're finding gradient of f, you have change in f over dx, change in f over dy, change in f over dz. So here I use grad v. So I have grad v over dx, grad v over dx times ex, which is the ex that we have here, grad v times over dy times ey, and grad v over dz times ez, which is what we have here. So if you want to get grad of v from this expression that we have here, we just divide dv by dom, which is dv by dom. So if you divide dv times dom, the dx will cancel, and then we remain with this, which is what we have here. Same applies to the second one. If we want the grad v in the y direction, we divide this, we divide, the dv over dom, and the dy will cancel, which is what we have here. The same as the last one. You did the same thing on the last one. So are we clear before we go to the other repair? Okay, so we move to the other repair, which is repair cylindric. So as I explained, we've got 4, but we're just going to do 3. The main ones, which is repair Cartesian.
I've got a question.
Yeah, sure.
Why do we have dx? Why do we have dx there down? Where is it?
Oh, sorry, that was a mistake. Sorry, that was a mistake. So it's supposed to be dz.
All right.
Yeah, supposed to be dz. Didn't see that. So yeah, we move on to the second repair, which is repair cylindric. So repair cylindric, it's almost, I won't say they're the same. So it's almost the same, as you can see from the drawing, it's almost the same as repair Cartesian. The only difference is that there's an addition of an angle here, an angle phi. Right, so we have the x-axis, we've got the z-axis, we've got the y-axis, and their base vectors EY, EZ, and EX, but we've introduced an angle between x, the axis x, and this vector right here, which is phi. So it's the same logic. So H is the horizontal representation of M. We just projected M downwards in the XY plane. What's different here is that on our projection of M downwards, we've added 2 other base vectors, right? So let me just write something. So this our line here, our line here is represented by, I don't know if you'll be able to see, rho. Wait, so we present this here by rho, and so the base vector of the line rho is E rho. And then, what else do you need to know? And then this base vector EC is as a result of this angle here. So as you know, this angle is going to rotate from 0 to 2 pi. So it's rotating from 0 to 2 pi. So this arrow is just this. So sometimes you'll be asked to tell the direction of arrow and EC and all of that. So this arrow direction is a tangent. So okay, the angle is moving around like this. So practically, rectangular surface here, OH prime MH is rotating to 360 degrees. So this rectangle here is rotating 360 degrees. So it's rotating that way. And then was to get the base vector arrow, you get the tangent, the angle, or to the direction of the rotation. So the angle is rotating, this angle is making this rectangular surface rotate 360 degrees. So the tangent to that is what we get as the base vector of that angle. So are we clear on that? So we've given this line a name. So we've given it rho. And then the extension of rho, we've given it the base vector E rho. And then we've said we can come up with this base vector EC from the rotation of the angle. So this angle right here, this angle is making this rectangular thing. You have to be a bit sure. So this rectangular thing is rotating around the x-axis in 360 degrees. So the tangent to that is what we get as the base vector. So the base vector of this angle here, phi, is EC, rotating in that direction. Are we together?
No.
Okay, what is the problem?
Just repeat what you just said on
Okay. Okay, so I'll repeat what I said. In repair cylindric, right? So we'll choose any point. I said it's almost like the repair Cartesian. The only thing that changes is that we add an angle phi between x and the extension, the line OH. So we add an angle phi that rotates from 0 to pi. So it rotates from 0 to 360. Right, it's around the x-axis from 0 to 360. So practically, the rotation of this phi angle is making this rectangular thing. It's like, I don't know how to explain. So this rectangular thing is rotating around the x-axis at 360 degrees. This triangle here, this rectangle, I mean. So this rectangle is rotating because of this angle. It's going to be rotating the z-axis at an angle of 360 degrees. And then we added two more base vectors. In that, we've given the name of this guy here, the distance from O to H, as rho. So the extension of rho is rho. That's the base vector. So the base vector is, okay, so the base vector of this line is rho. And then the way we get the base vector EC is from the rotation of the angle. The angle is rotating around the x-axis. It's rotating around the x-axis. So for us to come up with the base vector EC, we get the tangent to the rotation of the angle. So if the angle is, let me draw something. If the angle is rotating at 360 degrees, oh my God, 360 degrees. Forgive my circle. So if the angle is rotating at 360 degrees, we get the tangent to the circle. I know most of us know tangents. So the tangent to the circle is to the rotation, I mean. So yes, we get the tangent, which is what we have. So we're getting the tangent to the rotation of the angle. This angle here is making this triangle rotate around the z-axis at 360 degrees. So we get the tangent to that rotation as the base vector for this angle here, phi. So the base vector for the angle phi is going to be E. Am I clear? You can ask how.
So in our case, which one is the tangent now? Which point are we going to take as our tangent?
What? I couldn't draw this. I couldn't draw this tangent here just to show. So this whole thing, this whole triangular thing is rotating around the x-axis because of this angle at 360 degrees. So the tangent to that rotation is what I've indicated here as our arrow. So the tangent to the rotation of this angle, which is making this whole thing rotate around the x-axis, is this, and this is the base vector for phi, for our phi. So as we explained in the first one, so this OZ and HM are in parallel. So for this one, our Z doesn't change, but we have new base vectors, which are E rho and E phi. Am I clear? Okay. Yes. So we move. So now what we're going to try to do is try to express, try to get expressions for X, Y, and Z in the repair cylindric. We know that X, Y, and Z are in the repair Cartesian, but we're going to try to get the expressions of X, Y, and Z from the repair cylindric. So, which is what we're going to do right now. So for me to have X, I have my X-axis here, I have my Y-axis here, I have my X, my Z, and I have my rho, and I have my E rho, and I have my E phi. Right, so for me to have X, which is this, I have, we get the horizontal view. I want you guys to just get the X and the Y axis. So we're just dealing with the X and the Y axis and everything down here. So we get the X and the Y axis. And then for me to have X, I have my X here. So we have X here. We have our X. Okay, never mind. So we have our X. We have our X here, representing our X, and we have Y. So this Y and this Y are parallel, so they're the same. This line and this X, they're parallel, so they're the same, as we explained in the first part of the. So this line and this line are parallel. So this is Z, this is Z, this is X, this is also X, this is Y, this is also Y. So for us to get an expression of x in the repair cylindric, we have x and we have rho. So we're going to use trig now. We're going to use a normal trig mathematical expression. So for us to have x and us to have rho, this is our hypotenuse. This is our adjacent, and this is our opposite. This is the normal simple math that we know. So we have an opposite, an adjacent, and a hypotenuse, which is rho. We have our adjacent, which is x, which is representing the x axis, and we have our opposite, which is representing the y. So for me to have an expression of x, I have x and I have rho. So I have my adjacent and I have my hypotenuse. So I'll use cos, because cos is the one that has the adjacent and the hypotenuse. So I'm going to have cos phi is equals to x, which is my adjacent, over my hypotenuse, which is p. So I'm going to have cos theta is equals to x over my hypotenuse, which is phi. So if I change the subject of formula, I'm going to have x is equals to rho cos theta. Are we together? I'll explain again.
Kindly explain again.
How I got the x. Okay, so this x.
Wait, so just some clarification. Which one is the hypotenuse here, and which angle are we using for 90 degrees?
Okay, so we have x, y, and z. Let me just explain everything. So we have x, y, and z. All these are meeting each other at 90 degrees. That's why it's x and the x-axis and the y-axis meet each other at 90 degrees, and the z-axis meets the x and the y-axis at 90 degrees. So we have x, we have y, we have z. So we're going to forget about the vertical part of this, of the repair. So we're just going to be looking at the x and the y-axis and everything horizontal. So if we look at the x and the y, they're meeting at 90 degrees, right? But we have an angle here, phi. So we've come to say that this y and this line are parallel. So this, we're safe to say that this is also y. And this x, and we form the rectangle down here, and this x are parallel. So we're safe to say that this is x and this is x as well. This, as we explained, this is z. So we're safe, these are parallel, so we're safe to say this is z as well. But we're only doing it the down part. So this is a rectangle. So meaning x, this is y. We've concluded this is y because it's parallel with y. So the x and the y plane meet at 90 degrees. So we have our 90 degrees down here. Sorry about that. Yeah, we have our 90 degrees down there, here. And then here, our 90 degrees. So making this our hypotenuse. We know a rectangle. Let me try to draw it. A rectangle oh my god, okay, this is hard to draw, but a rectangle, when you cut a rectangle, has angles meeting at 90. So we have our y here, and we've concluded that this is our y as well. So we have our x here. We've concluded that this guy, a parallel, is also our x. So our x and our y meet at 90 degrees. Each axis meets another axis at 90 degrees. So our x and our y meet at 90, and our z and our y meet at 90. Our z and our x meet at 90, and our x and our y meet at 90 here. So having done that, we know that this is our 90. We know that this is our hypotenuse, and we use SOHCAHTOA from there. So SOHCAHTOA states, are we clear on the 90 degrees part? On which one is the hypotenuse?
Yeah.
Yes. So from there, we know our trig. So we have x, we have y, and we have rho. This is rho. This is not p, it's rho. Yes. So for us to have x, we use trig. So we have the adjacent. We're trying to find an expression of the adjacent. So we have the adjacent, which is x, and we have a hypotenuse, which is rho. So if we have the adjacent and the hypotenuse, we use cos automatically. So we have cos theta, cos this angle theta is equals to our adjacent, which is x over y. So if you have a book and pen, you can try to write that cos phi is equals to x over y. And then if you change the subtotal formula, you find that x is equals to phi times cos, is equals to rho times cos phi, which is what we have here as our expression for x in the reversed cylindric. I explain again.
I have a question.
Okay.
You said the x-axis and the y-axis are meeting at a point to form an angle of 90 degrees.
Yeah.
Where exactly are they forming an angle of 90 degrees?
Okay, so here you can see my pointer. Eh? Can you see my pointer?
Yes, I can.
Yeah.
Yes, so we have the x and the y axis. They're meeting each other at 90 degrees. Here 90 degrees. And we have the z meeting the y axis at 90 degrees. And we have the z meeting the x axis at 90 degrees. So it's like a corner of the room. Okay, let me make you imagine a corner of the room. So we have the corner of the room. We have two lines going, when we get down, we have two lines going the different directions, and we have one going up. So they all meet each other at 90 degrees. So we have our x-axis, our y-axis, and our z-axis all meeting each other at 90. That's established. So our x, our y in two-dimensional x and y also meet each other at 90 degrees. Even in three-dimensional, x and z meet each other at 90 degrees. So we have 90 degrees, z meeting x, we have z meeting y, and we have y meeting z at 90. C'est clair ou?
You spoke of parallel lines. You talked about parallel line that is meeting x, and that parallel line, you said we take it as our y, not so?
Yes, this line is parallel with this line. We formed the rectangle down here. So this line is parallel with this line. Maybe my drawing is not good. Okay, but yes.
So that line, the dotted one, is meeting the x at a 90 degrees.
Yes, it's meeting the x at 90 degrees. Yes.
So that's the 90 degrees that you're talking about, saying it's a perpendicular thingy. Then that's where we are going to use the cosine, whatever, where we have to take the adjacent and the hypotenuse. Also.
Yes, every axis meets another axis at 90 degrees. So if we assume that this y is parallel to this y and they're the same, so meaning this line is meeting this x-axis at 90 degrees. And if we assume that this is parallel to this, because we formed the rectangle, this guy, x, because it's parallel to x, is meeting the y at 90. And this is also parallel to this, of which we talked about earlier. So am I clear? So this guy here will be 90, and this guy here. So we have 90 degrees here and 90 degrees here. Then we have our angle here. Then we have our opposite, we have our adjacent, and we have our hypotenuse.
Can you please slow down where you're showing, you're pointing your, what's this? When you're moving your mouse, like the internet isn't that good. So when you're moving it very fast, I'm not able to follow which point you're even pointing at.
Okay, so but you got the fact that here we have a 90 degrees, and here as well we have a 90 degrees, because this, we've assumed that this is a x-axis because it's parallel with the x-axis. So it's meeting the y-axis at 90, and this is parallel with the y-axis. So it's meeting the x-axis at the angle of 90 degrees. Right. Okay. So if we have 90 degrees here.
Sorry, before you move on.
Okay.
The line that you said is meeting the x, this one, this dotted, this other dotted line that you said
This
is
one?
meeting the, which one?
Oui.
Not really. The other one?
This one?
Yes.
Oui.
Yes. What line is that? You said it's parallel to which line?
It's parallel to the x-axis. Okay, maybe my drawing is not.
Okay.
But it's parallel to the x. It's supposed to form, we're supposed to have a rectangle down here.
Okay, so you're saying we take that line as well as being parallel to the x-axis, as we are taking the other line to be parallel to the y-axis. Not
yes, so this line is assumed as the x-axis because it's parallel to the x-axis. We know parallel lines, the theorem about parallel lines. And then this guy here is also parallel to this guy here. So we assume this is also y. So this y is meeting the x-axis at 90 degrees angle. And this x is meeting the y-axis at the 90 degrees angle. Is that clear?
No.
Okay.
Like the lines, which one is parallel? Is it HY? The lines are they're just a lot. Is it H1 to M, and there is also H going to Y.
Sorry,
like,
okay, so okay, so this is this is not H1, this is just an extension of the dotted lines here of M. So it's an extension of dotted line. So it's just H. Yes. So as I said here, maybe my drawing is not so good, but when we plot this guy here, we're supposed to have a rectangle down here. So we have this, we have O to here, to H, to here, which is our rectangle. So this line, Y, the Y-axis, is parallel to this line here. And this line, the X-axis, is parallel to this line here. We know rectangles, the lines are parallel to each other, the line above and below and the lines in the sides. So which is the same concept that we're using here. So H is parallel to this, and X is parallel to this, which makes it X. Any more questions?
What about OM? OM is parallel to what?
OM. No, OM is not parallel to anything. OM is the vector OM, like from O to M. I was just trying to show you that it's not different from the Cartesian one. So this OM is the vector OM, the expression of the vector OM. And how, you remember how we got it in the Cartesian? We added this and this, or we added this and this. But now I'm focusing on the horizontal part, on the horizontal view of this. So forget the z-axis. You know that the z-axis is vertical. So I want you to look at it from the x and y axis. So from the x and y axis, we've got h, which h, we say that it's a movement of x direction in the direction x, and y direction in the direction of y, which made us plot this point H, like simple math. We have x plus y. So we move in the direction of x, and we move in the direction of y for us to get the point H. Right. And then we have rho. We have rho coming in from O to H. So we have this rectangle here. This rectangle here. And then rectangles, we know that this line is parallel to this line. And then this line is parallel to this line. So we assume if this is X axis, this will also be our Y axis. If this is the X axis and it's parallel to this line, this will also be our X axis. And this X axis is meeting this Y axis at the 90 degrees here. And this Y axis is meeting this X axis at the 90 degrees. And we have our hypotenuse, which is rho. Are we clear?
Yes, I'm clear. Just a minor concern.
Mm-hmm.
That thing that looks like a P, that is not a P, but it's just something that. Oh.
It's called rho.
Right.
So this is phi, this is rho. So if I wanted, I would have used X or R or M, but in almost all the books here, they use rho. So it's just, it's like a constant. Maybe from here to here, it's 2 meters. Yes, so we use rho. Usually here they use rho. Yes, so we've got, in repair cylindric, we've got an introduction of 2 vectors, or 2 base vectors, which is E rho, coming as the extension of the rho, extended, we have E rho, and the base vector coming from the rotation of the phi is E phi. And I said to say E phi is moving from 0 to 360 degrees. So it's this line here is being controlled by phi. This line, rho, is being controlled by phi. So we can have phi here. So meaning our H can change. Or so meaning, yes, meaning our H can, our position of H can change. So our phi is rotating at 360 degrees. So making this rectangle, the vertical rectangle, rotate at 360 degrees. So it's going to rotate around the x-axis, at 360 degrees. And then we get the base vector of the phi from tangent, like the tangent of the rotation of the angle is what we get as a result of our base vector. So our base vector of phi is represented in this direction. And then here our, what do I say? This is parallel to this. So this remains constant. This is still our Z. So we still have our EZ, E rho, and E phi. And we also have our EX, EY, and EZ. So now we have 2, what can I say? We have 2 referential points. From the Cartesian, which is EX, EY, and EZ, and then for the cylindric, the one that is being formed by this repair cylindric, which is E rho, E phi, and EZ. Yes. Any questions I've confused you more? Okay. I continue.
Yes, please.
Yes, so we got our X. I said here it makes a 90 degrees because this is Y, but it's parallel to the line Y. So it meets the plane Z at 90 degrees. So we used our SOHCAHTOA. We said we have our adjacent, which is X, and we have our hypotenuse, which is rho. So what trig function can we use? We said we will use cos. So cos theta is equals to adjacent, which is our x, over rho. So we want an expression of x in the repair cylindric. So we change the subject formula and we have x is equals to rho times cos phi. And then for us to get an expression of y, what we do the same thing. So we've said that this y and this y and this line are parallel, which makes this line y as well. So we have y, we have rho, and we have x, but we're trying to find an expression of y. So we have our opposite, which is y, and our hypotenuse, which is rho. So we say, the trig function that we use is sine. So sine is equals to opposite over the hypotenuse. So our opposite is y, because this y and are parallel, which makes this line y. So we have y sine phi is equals to y over rho. So when we change the subtotal formula, we'll find that y is equals to sine phi. And then this.
I've got a question.
Yeah, sure.
Yeah, you've said the x and the y, the angle which is there, it's 90 degrees, right?
The axes meet each other at 90 degrees, yeah?
Yeah. Then the phi also, it's the way you're explaining, it's showing us it's also 90.
The phi is showing that it's 90.
Yeah, because you're saying to take it as using SOHCAHTOA.
Yeah.
But how come? Because this line which is here, ought to.
This one?
Yeah. No.
Mm-hmm. This one? Oh, this one?
Yeah.
Rho.
Yes, the row.
Mm-hmm.
This one, it's cutting on the middle, showing the angle, it's 45.
Showing the angle, it's 45. Okay, I can see what you're saying, but what can I say? Maybe my drawing is bad, but as I say, this is supposed to be a rectangle. So this phi is, okay, the phi would have been maybe here, like if I drew a line here, maybe it's just bad drawing. But if my rho was from the center to here, maybe it would have looked so much like 45 degrees or what you're saying. But it still stands, this is not 45 degrees. It's not 45 degrees, it's just an angle quelconque phi that we do not know. And then these axes are meeting each other, are the ones meeting each other at 90 degrees. So we've got 90, we've got 90, we've got 90, we've got 90. It's forming a rectangle. And then we have a line cutting through the middle of the rectangle, which is rho. And then we have our 90 degrees here. So we can use SOHCAHTOA for us to find the expressions of x, y, and z. So for x, we've got x here, and we've got our hypotenuse. So we've got this is our angle. So this is the 90, this is our angle. So we've got
okay.
Yeah, so this is our 90, this is our angle. So if we use SOHCAHTOA, we know that we're going to have, if we have x as our adjacent and phi, and we're trying to get x, so we have an adjacent and a hypotenuse. For which trig function do we use? Following SOHCAHTOA, we use cos, because cos phi is equals to adjacent over hypotenuse. Our adjacent is x, and our hypotenuse is phi. Oh, is rho. Is rho. Yes, so when we change the sums of a formula, we have x is equals to rho times cos phi. The same is y. I said y, this y here is parallel to this line here, making this line y. So I assume that this line here is y as well. So what we're going to do is that we label it as y. So we have y. Oh my God. Okay. So we have y. So this is y. This line here is y. And then, yeah, so we try to find an expression for y. So we know that y is opposite. It's the opposite line to the angle. So we have opposite and we have our hypotenuse and we have our x, but we're trying to find an expression for y. So we say y, what expression, what trig function do we use if we have the opposite and the hypotenuse, which is sine. So sine is equals to opposite over hypotenuse. So we have sine theta, sine phi is equals to y over rho. And then when we change this other formula, we have y is equals to sine phi. C'est clair?
Oui.
D'accord.
C'est pas clear. I have a question with someone.
Oui.
Which angle are we using when finding y? Is it OH1? Is it OH1 or OY? Which angle are we using? Which theta?
We're using we only have one angle here, which is phi, this phi here. So we've said that this y, right? This y is parallel to this line, right? So we assume these parallel lines, you know the theorem about parallel lines. Parallel lines have got the same magnitude. So this line and this line, we assume that it's y, like this line is y because they're parallel with this y. So if we assume that this line is y, so now we have y, we have x, and we have phi, or rho, and we've got our angle phi here, and we have our 90 degrees here. So what I said is that using new trig, we have SOHCAHTOA, we have sine is equals to opposite over hypotenuse. And in this case, our y, the line y is opposite to this angle here. So we have y, we have sine phi is equals to y over our hypotenuse, which is rho. So for you to get an expression of y, you say y is equals to, when you change the sublet formula, because you have sine phi is equals to rho, is equals to y over rho. So when you change the sublet formula, you have y is equals to rho sine theta. So I repeat, this y here is parallel to this line here. And this x here is parallel to this line here. So we're safe to say that all the axes meet each other at 90 degrees. So where this y, our assumed y, is meeting the x-axis, it's 90 degrees. Where our assumed x, because it's parallel with this x, is meeting our y-axis, we have 90 degrees.
Oh, I see. I asked because the angle is not touching OY line.
The angle is not touching OY line. Yes, the angle is, this angle is an angle ranging from 0 to 2 pi to 360. So it can, when it reaches 90 degrees, it will definitely touch the y-axis because the x-axis and the y-axis touch each other at 90 degrees. But in this case, it's less than 90 degrees. So yeah, that's why.
All right, thanks.
Okay. So is it clear for everyone? I hope.
Did you explain on Z?
On Z, okay, yeah. Okay, so Z is equals to Z in that this Z is parallel to this Z. So, okay, what we're trying to do here, these expressions, X, Y, and Z, these are expressions found in the Cartesian. So now what we're trying to do is that we're trying to express X, Y, and Z in the repair cylindric. So X, Y, and Z in the repair Cartesian, X is equals to X, Y is equals to Y, and Z is equals to Z. But in the repair cylindric, because there is an addition of an angle and an addition of some new base vectors, the x is not going to be the same as in the repair Cartesian. So x is not going to be equals to x, y is not going to be equals to y. So which is I'm sure you remember how we expressed x and how we expressed y. So on z, this z is parallel to this z. And as you can see, this z is touching these, what can I say? These two base vectors. So this z is the same as this z. So the z doesn't change. The z is the same one because we agreed that parallel lines are the same. So this z is the same as this z. So the z doesn't change, but the x and the y is changed in expression. So in the Cartesian form, x is equals to x, y is equals to y, z is equals to z. But when we come to repair cylindric, the x and the y changes, but the z remains the same.
All right.
Wait. So we try to move.
Sorry to take you back. Which one did you say was our opposite and our adjacent again?
So we have our 90 degrees because we've assumed that this is y as well, right? Yeah, so if this is y and this is x, so we know that touch to that 90 degrees. So we have a 90 degrees here. So if we have a 90 degrees here, we have our angle here, we have our opposite, we have our adjacent, and we have our hypotenuse, which is rho.
Okay, thank you.
Right. So this is why our opposite is y. Our yes, our opposite is y. Our adjacent is x. So we move on, I believe. So we move to. So don't forget that this line is rho. So we have represented this line by rho. So we move to the expressions of E rho. A minute. So we're now going to express E rho and E phi. We're going to get the expressions of E rho and E phi. So we have the expression of x, y, z. Now we've moved to the expressions of E rho and E phi and Ez. So how do we get the expression for E rho, E phi, and Ez? So I've written something here. It's the horizontal view. So have to be visual. So this is my x plane. Oh, this is my y axis. This is my x axis. Do you guys get that? This is my y axis. This is my x axis. It's like I've just written it. This is my y axis. This is my x axis. And I've just written it here. So this is my y axis. This is my x axis. And then what I'm going to do here, for me to get expressions for E rho, E phi, and Ez, I have to project these bases from the center. So this, I move, what can I say? I move the H, I move H to O. I move the point H to O. So if I move the point H to O, this will join in with Z, which will just be the same. But this guy will go like this, and this guy will come in like this. Do you guys copy what I'm trying to say? Or I explain again?
Negative.
Kindly explain again.
Okay. So what I'm saying is that for me to get an expression of E rho, E phi, and Ez, what's going to happen is that I have to project this point here, because I have Z, I have E rho, E phi, and E rho. So I'm going to this point H. This is just H. This one is just an extension of the dotted line. So this point here, I'm going to have to move it to O. So if I move this whole point here to O, H and O are combined, this H is going to be in the same direction as Z, or this line HM is going to be in the same direction as Z, which we've already said is the Z axis, and the base vector is EZ, and then these other two bases, if I move this point, I put it here, the same with I'm not changing anything. So this line is going to go in the same direction this side, and this line is going to come in the same direction this side. Okay, I will explain again. If I move, I'm trying to get an expression of E rho, E phi, and EZ. Right, so I'm trying to get an expression of E rho, E phi, and EZ. So what do? I have the base vectors are here. So at the point H, the meeting at the point H, we have we have Z, and then we have E rho, E phi, and E rho. So what do? I move this point here, I project it at O. So I project this point at O. So meaning everything here is going to move to the center. So this E phi is going to be remain in the same direction. E phi is going to be going like that. And then our E rho is going to still be projected in this direction. Do you guys copy?
Yeah, it's clear.
Yes, which is what I have here. So I just drew it simple here, I hope it doesn't confuse you. So it's the same as this X and Y is this X, is this Y and X. And then I've moved this point to the center. So this was our O, this is our O, where X and Y meet. But I've moved this guy here to the center. So I'm going to have E rho in that direction, the same direction, and E phi, in that direction, and E rho in the same direction. Do you guys copy?
Yes.
I explain the diagram again. This is Y, and this is X. So this is what we have here. We have Y, and we have X. It's the same thing, like X and Y axis. Yes, math X and Y axis, but they're just facing the other direction. So I have Y and X axis meeting at O. So I want an expression for E rho, for E phi, and EZ. So what do? This point here, I move it to the center. So if I move this point to the center, the direction is not going to change. The direction of the base vectors is not going to change. So if I move it to the center, this guy here, the base vector E phi, is going to be in the same direction. The base vector E rho is going to be in the same direction, coming down like this, which is what I have here. So I've moved them to the center. My E rho is going to be in the same direction, and my E phi is going to be in the same direction, and my E rho is going to be in the same direction. And then we've noticed that the angle separating the axe X and the axe E rho, which is this whole thing, we have rho here, and the extension of it, the base vector of this whole line is E rho. So the angle separating these two axes is this, phi, which is what we have here. And then in math or whichever subject you learned it from. So we know that using our angles, this angle here is the same as this angle here. Or first, let me deal with this angle. So we have this angle. This angle is separating the x-axis and the E rho axis. So we have this angle here, we have our x, we have our E rho after projecting it at zero, at O, at the center. So we have this. So for us to get an expression of E rho, from here we can tell that our E rho is the hypotenuse, right? So our E rho has become a hypotenuse, and then our x is an adjacent. And then this line here, we form a dotted line because we want to be, like we're trying to use trigonometry. So we form a dotted line, which is our opposite. And then we've noticed that this is the same as this, as in this line here is parallel to this line here. Is it clear or no?
So clear.
Yes, so this line here is parallel to this line here. And then we have x, we have this that has formed a hypotenuse. So what we do, we use our same trig functions. And then what we have is, so, okay, I don't know if we learned this, but I didn't learn this from Zambia, I learned it from here. So our opposite trig, our opposite is sine, is a representation of sine, and our adjacent is a representation of cos. So what we're going to do here, we have euro. So for us to have adjacent in trig, we have c squared is equals to a plus a squared plus b squared, which is the same thing that we're doing here. So we have euro is equals to x plus this guy here, which is parallel to y, which we can safely say that it's y. So we have x plus y is equals to euro. Then what we're going to have is x is going to be, this is the adjacent, So we have adjacent cos phi in the direction of ex. We know the base vector of x is ex. Yes, so we have cos phi in the direction of ex plus the adjacent, this line is parallel to this line. So we're safe to say that this is our y, and our y is opposite. So the opposite is equal to sine phi times our y. We know the base vector of y is ey. So we have cos phi in the direction of ex plus sine phi in the direction of ey as an expression for euro, which is what we have. Any questions?
Explain again.
Okay, but do you get the point where I moved this h to the center?
I get it.
I can get you.
Yeah, I get that point.
Yes. Okay. Now, this guy we have this. This is our center. Sorry, I forgot to indicate the O. So this is our center where we've projected our this. So we have our x, we still have our x, we still have our y. Just like here, we have our x, we have our y. And then we know the base vectors for x is ex, which is this, what I indicated here. And our base vector for y, we have this. Our base vector for z is ez. So what we have here, we have euro as the hypotenuse, because we just have to make a dotted line here. And we know that this line is parallel to this line. This y is parallel in this line. They're going in the same direction, and yeah, all of that. So we have this y represented as this, and then we have our x, and then we have our euro. So now we're trying to get an expression of euro. So in trig, we know that our hypotenuse is equals to our adjacent plus our opposite. So our adjacent, or our hypotenuse is euro. What's our adjacent? Our adjacent is x. Our hypotenuse is y. So we can't write x ex plus y ey. So we have to find, we have an expression for adjacent. Expression for adjacent is cos. So adjacent, the adjacent side is represented as cos. So we have cos c in the direction of ex plus opposite as sine. So we have plus sine c in the direction of ey, because we know that this and this are the same, and the base vector for y is ey. So you have to remember that for opposite it's sine, adjacent it's cos. And then here for euro we have x plus y, and then our x is cos phi and then our y is sine phi. So now we have our expression because it's moving in the direction of x. So we have cos phi ex plus sine phi ey. C'est bon?
Oui, c'est bon.
Oui, c'est bon.
Oui.
D'accord. So we move to what's this? E phi. E phi, which is this our angle here, which is this angle here. Or this line, I mean, not angle, this line here, E phi. Our base vector E phi. So we have E phi. Okay. So now our E phi, which is this, can also be represented as a hypotenuse. Okay, and then I want you guys to notice one thing. This x and y are meeting each other at 90 degrees, and this and this are meeting each other at 90 degrees. Okay, so with that being said, I have my E phi here, which can be represented as the hypotenuse. So I draw a line, decide to make an angle. So I have my phi here. So using angles, this angle here is the same as this angle. So we can either make a Z angle here. We know that this angle is the same as this angle, or this angle is the same as this angle. Yeah. So we have this angle here that is the same as this angle. So we can find our expression of E phi. So if we form a line, and if, let me try to draw something. So here I have an extension of x. I have an extension of x in the opposite direction. So I have negative x. So this is an extension of x in the opposite direction. So we know that when we extend this y in this direction, just like the normal x or y plane, when we extend it, this is our center. So we extend this side to be negative. This one, when we extend this side to be negative. So we have our E phi, and our E phi, we have our hypotenuse, we have our angle, we have our, what's this, our adjacent, and we have our opposite. So in this case, what does the opposite indicate? How do I phrase this question? What is the opposite? What's the opposite? Can someone help us?
It will be negative x.
Thank you. So we have negative x here. So we have our expression of E phi will be this, our adjacent plus our opposite. Now we know x, the base vector of x is EX. So we have E phi is equals to negative, because it's in the negative direction. So we have, and we know that opposite is sine. So we have negative sine phi in the direction of EX plus, this is still positive, plus cos phi in the direction of EY. Is that clear or no?
It's clear, but I've got a question.
Sure.
Yeah, can you, since this one, the first one, it's E, can you differentiate this one to find the E phi?
Can you differentiate what? Yeah, sure. If you really do not know how to do this thing here, you can just, when you have your E rho, you can just differentiate your values of E rho for you to get E phi.
All right, thank you.
Yeah, so your differentiation of cos is negative sine in the direction of EX plus your differentiation of sine is cos in the direction of EY. So yeah, you can use that, but just to better understanding for you to know where it's really coming from. Yeah, you can do this.
All right.
Yeah. Then our EZ, our direction EZ, since we brought this guy here, where's my spotlight? Okay. So we brought this guy here at the middle here. So this line is running through this line. Right, so our EZ will be the same. As I said here, our Z is the same, our EZ also. If our Z is the same, we know that the base vector running through Z is EZ. So our EZ will also be the same. So having had that, we now go to our expression. Oh, I think, let me see. Okay, so having had that, will end when our time is up. So having had that, we get our expression for OM. OM is equals to OH plus HM. Let me go back to the drawing. So our, oh my God, okay, so our OM is equals to, OH plus HM, the same thing. But here, the difference is that this is rho. So we have, this is not P, sorry about that. So we have, yes. So we have rho. So for us to get our OM is equals to OH plus H prime. So we have OH, which is rho, in the E rho direction. HM is Z in the EZ direction. Are you guys lost or I repeat that?
No, okay.
Yeah, okay. So our OM, we're using this direction. We're using this direction and this direction. Or we can use this direction and this direction because this is parallel to this. OH is parallel to H prime of M. So this and this are the same. So this is rho, this is rho. So we've chosen to use OH to H prime. So we know that from O to H, this is rho. Rho in the direction, because this is a vector, so you're not supposed to forget the direction. So rho in the direction of E rho plus OH to M in the direction of Z. So we have Z, EZ. Z direction, Z in the direction of EZ, which is our OM. In coordinates cylindric. So in coordinate Cartesian, OM is equals to X, EX plus Y, EY plus Z, EZ. In coordinate cylindric, OM is equals to rho, E rho plus Z, EZ. So you're supposed to know these things by heart. So we move. So just a moment. Okay, so we have this, but we have an expression for E rho that we're from finding here. So what we do is that where there's E rho, we replace with this. Yes, so where there's E rho, we replace with this, what we have here. So which is what we've done here. So we replace with this. So we have rho times cos phi EX plus rho sine phi EY plus Z EZ. Are you guys lost there? Or what together?
What together?
Yeah, together.
Okay.
What together?
D'accord. On y va. So we have that and that, which is our expression of OM. So if you want, you can leave it in here. Okay, but usually we have, you leave it in here, but the expression, the finished final expression of OM in coordinate cylindric is rho cos phi in the direction of EX plus rho sine phi in the direction of EY plus Z in the direction of EZ. So yeah, so we're just going to finish this part. So DOM, when getting DOM is a bit complicated because we have to use product rule. This is a constant as I explained. So for us to get this expression that we have here, these dots that you're seeing on top, it's equivalent. So if I say rho, what's this, phi point, it's the same as d phi. It means that rho has been differentiated once. So this rho point, it means that rho has been differentiated once. This z point means that z has been differentiated once. Yeah, so for us to have DOM, as I said, is the derivative of OM. It's a change in OM, the change, okay, yeah, the derivative of OM. So for us to get that, I think this will be the last part we'll do. So for us to get that, okay, so for us to get the OM, just a minute. Okay, for us to get the OM, there's a procedure that we do. So we know that if E rho is equals to that, which we're just from finding, and E rho, if E is equals to this, and EZ is equals to this, and we've established our OM and everything. So for us to get our DOM, first we need the differentiation of E rho is equals to, okay, so the differentiation of E rho, okay, I think we'll end here, unless you guys want me to continue.
No.
No, we have to pause a bit.
Okay, so we'll continue on Thursday because this, we have to do the differentiation of this, we have to do the differentiation of this for us to actually get to our DOM, which I believe we can do in 2 minutes. But yeah, so this is practically how you get to some expressions. And yeah, the next time we'll do our coordinate spheric and we'll start our main what do you call it? Our main module, which is, we start from what the Coulomb and we'll move on from there. So yeah, thank you for attending, and I advise you guys to really revise through these things because these things are very important, especially for the people going to do GGM, NSA, NSAM. I think for NSAM and NSA, it's actually even more advanced. So you have to really practice, you have to be visual and all that. So you'll go through what we've discussed today and yeah, and you'll be good to go. Just try to be visual and try to go through what we've gone today. And on Thursday, we'll finish up with the rest, inshallah. And
do you mind sending us a
You
copy?
haven't sent this document yet.
What?
This document, you haven't sent it.
The what? The PDF?
Yes.
Oh yeah, I'll send it immediately. Well done. I'll send it to you guys.
All right, thanks.
Yeah, thank
Are
you
we
very much
allowed
for
to do
attending.
follow-up questions?
Yeah, sure, allowed to. But I that this module, it's not this complicated. It's mechanic du poids. This is just a part of it. So we're just using, like I've just been talking about this because we're going to be using gradients, we're going to be using some expressions of dV, ds in our module, but it's not really, yeah, it's just like the surface. We're just going to be using some expressions, but I just couldn't come and tell you guys, no, these are the expressions we're going to be using. I had to explain where they're coming from and how we came up with them. So yeah, thank you very much and have a blessed day.
Oh, so wait, you said for those doing answer, it gets a bit more advanced. So do you happen to have any material we can use in our own free time?
Yeah, I can talk to some of the guys who I know are doing answer. They can send you some PDFs and stuff. But tomorrow, I believe you're doing mechanic du poids. So Charles will really explain and he'll talk about maybe the differences that are there. But this is like the base, so everyone does it.
Okay.
Yeah. Thank you very much.
All right, you're welcome.
All right.